Okay, so we're looking at this study. This is the third video on this study because I'm trying to explain everything. It's taking a little longer than what you would have on an exam. But we're trying to see, is there inequities at this Harris Bank? At last time, we did an overall F test to see if any of the variables had any utility, and they did. And the second one is, do the interaction terms, are they necessary? That is, are they confounded? Are age, education, experience confounded with the gender part? So now let's just kind of answer some questions here in context. So we're looking at Model 2, state an interpretation for the following regression equation of the natural log of the bank and salaries in context. Well, it's 0.0170, so for otherwise equivalent employees, each additional year of education corresponds to a 0.017 increase in the natural logs of bank salaries. So one of the things you want to make sure you include is otherwise equivalent, or all the other variables kept constant. Another nice thing is to say on average, because the regression equation is sort of like the average response. Okay, let's try the other one. 0.0141 for males. For otherwise equivalent employees, the males average 0.141 for natural log of the bank salaries. Now, this is a little bonus question here. Since it's the natural log of the bank salaries, you could put 0.1017 and get 1.07. So 1.71% earnings more for each year of experience, whereas if you put in the one for females, males earn 15.11% more than females. So I think that's, at least that might be some indication that there's gender inequality. And though we would like to say there isn't in this world today, I think some of the statistical studies say otherwise. Now, why would it be inappropriate to use Model 3 for testing whether the males' bank salaries and average are more than females? So let's take a look at Bank 3. Bank 3, okay, so here's Model 3. It just takes a look at seniors and males. Well, you're taking out education experience. And so really what's happening is that the age, education, experience seems to have some effect on the natural log of the bank salaries, or just the bank salaries. So I think what you want to write is that gender may be confounded with these other ones. We need to adjust for them in Model 2 for a fair comparison. So that's something to kind of keep into effect. It's not so much that the slopes might be changing, it might be where you're starting from might be changing. And so so confounding variables might be an indication or an explanation for the change in salaries. All right, so let's try this next one. Conduct a single test whether the males are on average more than females. Conduct your test at 1%, show your work, and interpret results. So this kind of question up here is supposed to help you decide, okay, which model do I use? Do I use Model 1? Well, no, because we got rid of the interaction effects. Should I use Model 2? Model 3? Well, question E told us that Model 3 might have confounding factors, and Model 4, we don't even have gender in here, so that doesn't really help us very much. So we should look at Model 2. Actually, we should use both Model 2 and, well, in this case we only have to use Model 2 because we only have to use a single test for this. And so once we set up the null hypothesis, our null hypothesis is that the beta male is less than or equal to 0, and our alternative hypothesis is that beta male is bigger than 0. You could say that this is set equal to 0. We've kind of had conversations for that. Now, if you take a look at Model 2, and let's just kind of remind ourselves we're going to look at Model 2. If you look at Model 2, you can see that for the male, the coefficient is 0.4150. And the standard error coefficient is that. So we can get the t-value off of this. I mean, if you wanted to, you could write t is equal to 0.14051 minus 0 over the standard error, of 0.02332, but that's going to give you 6.02 for your t-statistic. So, well, I wrote it. You don't have to write it. So if we draw the picture to kind of help us give us an idea, 6.02 is way out here, so our p-value, because it's greater than, we can do this. Now, we can't use the p-value on Minitab because we only have one-sided. So let's go ahead and calculate the p-value. This is going to be t-CDF of going from 6.02 to a very, very large number. You can just put in a very, very large number. And now we have to figure out the degrees of freedom. If you just kind of remind yourself what the degrees of freedom are, you're looking at this statistic, and so you go down here for the residual error, and that will give you your, I'll put that in green, your degrees of freedom. So our degrees of freedom will be 87, and that's about equal to 0.000002. And if we wanted to go on to Minitab, we could do the same. Go to graph, probability distribution plot, view probability. We want the t-test. We've got degrees of freedom of 87. We want the shaded area bigger, the right tail of 6.02. And it's going to be a little bit different, but we're dealing with such minuscule numbers that's okay. We get, well, 2.21 with 8 zeros. So 7 or 8 zeros. So in other words, what we conclude then is that the data, make sure again you put the degrees of freedom when you calculate this, the data, this is also much smaller than 1, and not just a little bit, it undershoots it a lot, so I'd put compelling evidence that on average males will have a larger natural log of the bank salary than an otherwise equivalent female. Okay. So there is a main effect due to gender. Now let's go ahead and obtain a confidence interval for the average amount by which the male's bank salaries logarithm exceeds the test in part H, and write a sentence or two to properly to interpret your interval in a way that's correct in which a layperson can understand. All right. Now, we could at this point, by the way, test to see if there's a main effect due to some other things. Rather than beta male, we could go ahead and look at the beta of education or beta of experience to see if that's a main effect. We just don't have the Minitab output to do that. All right, so let's go ahead and do this confidence interval. Remember what we have is we have the estimate plus or minus the multiplier times the standard error. All right, so our estimate for the male was 0.414051. You can see it up here. Plus or minus the multiplier. Our standard error turned out to be this 0.0232, so I guess it was good that I kept that around. But the multiplier, we're going to have to figure out what that is. All right, let's go to the side here. We've got a t-statistic, which is pretty good. We wanted a 99%, so we got 99%. And so I want 0.01. So I guess what I want to do is to do the inverse t of 0.99 with 87 degrees of freedom. Remember, the 87 was up there. And so remember how you do this. Okay, if you had a calculator that actually had power, we could do this, but I don't. It's too bad. So we'll go to Minitab and go to Graph, Probability Distribution, Plot, View Probability. Okay, I want a t-distribution, 87 degrees of freedom. Did I put 84 last time? Uh-oh. 87 degrees of freedom. I want the probability, and I want the probability in the right tail to be only 0.01. If I want to do the left tail, I put 0.99. If I go ahead and calculate that, I get 2.37. So the multiplier is 2.37. And so put in this 2.37, you do the calculations. Oh, not a plus minus, it's going to be a minus because I just wanted one-sided. And so this is my estimate, so I have to go down to kind of do a little bit of cushion in there. And if you go ahead and calculate that, the beta male is going to be bigger than or equal to by 0.085. So males on average earn at least 0.085 logarithmic of bank salary than equivalent females. And so for a little extra credit, again, you could do the 0.085. You would calculate at 1.089, so it's greater than about 8.9% for males, at least at Harris Bank. The one with the lion on top. Okay. All right. So these are some example problems of what you may have to do is kind of go through the process of this two-way ANOVA. And so remember, kind of the big sort of structure that you have is, first of all, you see, well, the overall F-test kind of says, does any of these predictors have any value? But then the question is there any interaction between the two? Does one factor depend on another factor? So you might want to kind of just write some question. Does the effect of dorm depend on the level of state that you're from? Or does, just some questions along those lines, and that's the question of interaction. Once you have determined to eliminate the interaction, write your new model with no interaction terms, and then determine whether it's a factor 1 or due to factor 2. And this might have a variety of betas. There might just be more than one beta that's 0, in which case you might have to use the partial F-test, or 1, which you can just simply use the t-test. But these answer some very big questions as far as, does one thing cause another one? And so these are some great questions to respond to statistics, can help us along those lines. Okay.